So here we are going to learn how we can derive a POS, product of sum expression, in its canonical logical form, and also use K-map to come up with a simplified expression, and then using that expression to implement NOR gates to come up with a circuit diagram. So on the left you see a truth table, and it says for the logic function f with three inputs x, y, and z described by the following truth table for the POS form, implemented using only NOR gates by drawing the logic. And one of the ways you can do it is by applying De Morgan's law. In this video we will actually use both the canonical logic form and also the simplified expression from K-map to implement the circuit using NOR gates only. So let's look at the max terms right here. We have one of the max terms over here, we have another one over here. So we have basically a total of 3 max terms. This represents a code for 0, this is 3, this is 4. So if I write the expression f equals to, again this is the canonical logic form, f equals to, so this is going to be x plus y plus z. This one is going to be x plus y bar plus z bar, right? And this one is going to be x bar plus y plus z. And we know canonical logical form, this is the POS. So this is going to be a product of these three sum. So x plus y plus z, and then we have x plus y bar plus z bar, and then we have the last term which is for the 4, which is x bar plus y plus z right here. So just like we did in I believe it was lecture number 8 when we took an equation and implemented using NAND gate only, we're going to do something very similar over here. And just for the sake of easiness, I'm actually going to break it into 3 terms. Okay, so say this thing right here is my term A, okay, this is my term B, and say this is my term C in the equation. Okay, so alternatively I can write it down as f equals to A dot B dot C, correct? Now also I can write this equation as A dot B dot C and then have 2 bars on it. Okay, we know that if you have 2 complements on top of each other, they will basically cancel out. So this is equivalent to this thing right here. Now in this equation right here, I can apply De Morgan's theorem. Applying De Morgan's theorem. And if you remember, one of the rules that we learned from Boolean algebra laws and rules and De Morgan's theorem, that you can only break 1 bar at one time. Okay, so I'm going to start off with this bar right here, and I'm going to open this bar. So this would mean I basically have what? I basically have this right here. Okay, so I'm going to write it down as A dot B dot C bar on the whole thing. According to the De Morgan's law, it is equivalent to saying A bar plus B bar plus C bar, correct? Now what I'm going to do is actually replace the values for A, B, and C. Replacing values for A, B, and C. Okay, so what was A? A was over here, x plus y plus z, x plus y plus z, and because I have this bar over here, so I'm gonna have to have a bar. Then I have plus sign, this right here, followed by B bar. B is this right here, x plus y bar plus z bar, and then bar on the whole thing. plus we have C here now, C bar. So C is equivalent to this right here, and then bar on the whole thing. So I get X bar plus Y plus Z, and then bar on the whole thing. And because now I have this bar right here, which was on the very top, right? So I'm gonna put this right here. All right, now if you notice, this actually makes a NOR gate right here, okay, because you have this plus sign and then you have inward sign on the bar on top of this thing. So let's make a NOR gate. This makes another NOR gate right here. This makes another NOR gate right here, okay, and this whole thing right here, this whole thing makes another NOR gate, correct? Yeah, so in other words, what I could do here, I can have 3 NOR gates, NOR 1, NOR 2, and NOR 3. Let's work on that. So this is going to be my NOR 1. Okay, what are the inputs to that? X plus Y plus Z. So those are going to be X plus Y plus Z. Let's work on NOR 2 now. Okay, what are the inputs to that? Those are X, Y bar, Z bar. Okay, X. And then if you want to make inverter using NOR, you basically need Y wire and then short it. Okay, so that's Y bar right here, and then also you have Z bar. So similarly you do the same thing over here. Okay, this is your Z, this is NOR 2. Now I'm going to work on NOR 3. The inputs to NOR 3 are X bar. So I'm gonna have to run the wire X through in NOR to make an inverter. As you can see over here, how you make inverter, you basically have take one NOR and then short the signal, okay, because a NOR is a 2-input gate. So this is your X bar, this is going to be a Y, and this is going to be a Z. So you have Y here, and then you have Z here, and then this NOR, which is for the bar on the whole thing, okay, NOR 4. So and the inputs to that are NOR 1, NOR 2, and NOR 3. So you connect the output of NOR 1, NOR 1, NOR 2, and NOR 3 to NOR 4, and that is your F. Now notice here, everything is NOR gate here. The whole circuit diagram is made up of the NOR gates, okay? And this was when you were using the canonical form, canonical expression, okay? This is from the canonical expression. Now say you were going to do the same thing, but with the simplified expression from the K-map. Okay, the first thing we need to do is to put our max terms into this K-map. We all know that we have 0 here, 1 here, 3 here, 4, 5, 6, and 7. That's how the arrangement of the cells is. The two most significant terms, least significant terms are YZ. Most significant term is X. This is our function F. We have 0 here, 1 here, 0, 0, 0, 1, 1, 1, and then 1, 0. Remember, we are doing POS here. Okay, so what would be the expression here? Let's put the max term first. It has 0 here, 3 is 0, and 4 is 0. So this should be an easy choice. We will go with 0 and 4, okay, and the term for that would be vertical 0. That's 2, 0, 0, and 4. Actually, there's no common here, Okay, the only thing common here is this thing right here. So this will be y plus z. Okay, yeah, and then this guy right here is gonna make x plus y bar plus z bar. Okay, that is my most simplified expression. You don't have to do further simplification here. So I'm gonna copy this thing right here and then paste it somewhere at the bottom. The expression above here. So now we are going to work on the NOR implementation of this logic circuit diagram. And again, you could do the same thing just like I did over here for the canonical logic form. You can simply just have two bars on top of each other like this, and then you can break one bar at one time. So I'm going to start with this one right here, and again, if I label this as my A term and this is my B term, remember you don't have to label them as A and B. This is just for the sake of the easy explanation. If you do more and more practice, you'll get expert and you don't have to do those do those things. Now I'm going to rewrite the equation as, so F equals to A dot B, and then I have the bar on the whole thing. Okay, I'm not including this top bar at this point right here. Okay, I'm only including this bottom bar. Now we know that this is equivalent to what? This is equivalent to A bar plus B bar, correct? All right, now replace A and B with their values, replacing same thing. Okay, replacing what we did over here, replacing values for A and B. So we get what? So we get F equals to, what was A? A was y plus z, and then we have bar on the holding, plus, because we have a bar here, plus B bar. What is B? B is x plus y bar plus z bar, and then I have bar on the whole thing, right? Okay, and then I'm going to put the top bar, which was right here, right? This top bar, this comes over here. Okay, now notice here, this is one NOR here, so I'll say this is my NOR 1. This is another NOR here, correct? Because all the terms are being added, plus you have this bar on the whole thing, so this makes NOR 2. And then I have this this whole thing right here. Okay, this makes another NOR gate, so I'm gonna leave it as NOR 3 because we are adding it, and then we have this bar here, correct? Okay, all right, let's make a circuit for this now. I'm going to start off with the NOR gate, NOR 1. Okay, so this is my NOR 1. Okay, NOR 1. What are the inputs to that? The inputs are y plus z, so that should be simple y and z. Then I have NOR 2. NOR 2. The inputs here, I'm gonna replace this over here. So inputs are x plus y bar plus z bar. So here's your x. Y bar is going to be this right here, going through inverter, because that's how you make an inverter. Also you have z here, and then goes to an inverter through a NOR, and then signals are short. Plus we have the last NOR, which is NOR 3. The inputs to the NOR 3 are these two terms. Okay, so the output of these two will go into this NOR right here, and I'll label it as NOR 3, and that's your output function F. Okay, so another way could have been possible is you take this expression right here. Okay, you use the AND gates and OR gates to come up with a logic diagram, and then wherever you have AND gate, replace it with this, or wherever you have OR gates, you can replace it with two consecutive NOR gates. Okay, but the hint is the apply De Morgan's theorem, because that is the quickest way of doing it. I hope you learn how to drive a POS expression in both canonical form and also the K-map expression form, and then take it from there, apply De Morgan's to come up with a simplified expression and implement the logic using NOR gates. Thank you for watching. Bye.